Okay, everyone, can you figure out what we're going to do next? We, of course, in Calc 1, we did areas under curves, and then this, in Calc 2, we've done volumes of revolution, and we've done lengths of curves. Can you kind of see what is yet to do? We're going to do areas of revolution. By that, I mean you've got some sort of a function as before. Here's your x-axis. And here's your y-axis. Got something, let's say, looks like this. From A to B. Guess you might as well make it stop right there. There we go. So there's the function f of x. And given that curve right there, we're going to take that curve and go all the way around the x-axis with it, back up the other side, and we'll generate a surface. Agreed? That'll generate a surface, and we want the area of that surface. Okay? So how do we go about doing it? Can you kind of see what you might want to do? Let me first tell you what I did the first time I taught this course. I was teaching at the University of North Dakota. I was teaching Calc II, which is this course right here, and this particular section wasn't in the book. But I wanted to just kind of give the students something a little bit extra, so I just gave them this lesson. I said, well, here's the obvious answer. What do? We take a little dx like this, or call it a little delta x, and then this length right here would be close to delta x. And so the distance all the way around that you get by taking this little segment going all the way around would be this width right here, which would be delta x or dx. I'll call it delta x. And then you do what? That would be the width, and you multiply that by the distance around. And what's the distance around? It's going to be it's going to be the length of the circumference, and the circumference is 2 pi times the radius, and the radius, of course, is just the height of the function. So that would be 2 pi times the radius. There's 2 pi times the radius. There's the circumference multiplied by the thickness, and you add all those things up, and that gives you an approximation for the surface area. And then if you want the exact value for the surface area, you take the limit of this as delta x gets smaller and smaller. Goes to 0, and you would end up with the integral of, and you can bring the 2 pi out front since that's the constant, of f of x times dx. 2 pi f of x, 2 pi times f of x times dx. There it is from A to B. Okay? It looks reasonable, doesn't it? Doesn't that look reasonable? 2 pi times the radius, that gives you the circumference, and you multiply that by your thickness, and you're all set. So what's wrong with that? It's wrong. I found out a little bit later when I actually went through and studied all the Calc 3 material, and I realized I was wrong. Can you see what's wrong with it? Why isn't that solid like our previous arguments were? It shows the problem with depending too much on your intuition. If you just kind of depend on your intuition without actually solidifying the result using rigorous proofs, you can get caught in mathematics. And as I say, all these things I'm showing you, we're not doing them rigorously. We're kind of depending on intuition. But this one, my intuition led me astray. Can you see what was wrong with it? To show you what was wrong with it, let me do another example here. I'm going to erase this for the present. And I'm going to ask, if you have, say, something like this, and you want to travel from here to here. Well, let's take this line right from there to there, the diagonal line. Okay? Let's think about two different things. If you want the area underneath this thing, all you have to do is to take these little rectangles, like so, I'm going to start making them wider just so I don't spend too much time doing it. There you go. And what? If you make the widths of these rectangles get smaller and smaller, then all of these rectangles are going to converge. The area under all those rectangles is going to converge to the area underneath this diagonal line. Agreed? You got a little bit left off here, but as soon as you start making them smaller, you're going to grab that piece, and you're going to grab that piece, and you're going to grab that piece, and then you keep making them smaller yet. You're going to keep grabbing more and more of the area, and you're going to converge to the area underneath that diagonal line. So that's what we did back in Calc 1, and that shows that the limit of these rectangles does in fact give us the area underneath this diagonal line. On the other hand, what if I wanted to travel along that diagonal line? If this length is 1 right here, and this length is 1, then we know that the length of this diagonal line from Pythagorean's theorem, that length of that diagonal line is square root of 2. So let's do the same sort of thing. If I wanted to travel from here to here, I could first go from here to here and here to here, and that's going to be 2. But what if I travel much, much closer to this diagonal line? What if I go right along here? See what I'm doing? I'm going right along this little path. I'm staying really close to that diagonal line. What's going to happen in the limit as I keep making smaller and smaller little jagged edges there? Well, look at it. It doesn't matter. It doesn't matter. No matter how close these little jagged edges get to this diagonal line, what's the distance that I'm going? Am I getting closer and closer to the square root of 2 as I stay closer and closer to this diagonal line? No, look at here. I'm always going either to the right or I'm going up. And so I add all those lengths going to the right and I add all those lengths going up, and all the lengths going right are going to add up to 1, and all the lengths going up are going to add up to 1. So it doesn't matter whether I first go like this or whether I do all the way. Either way, the total is going to be 2. Agreed? Just like going across town. If you have to go from here to here and the streets go like this, it doesn't matter whether you do a that wasn't very good, a trip like that or a trip like this. You're going to end up going the same distance. Okay. So so my point is this: that you need to be really careful that as you take the limit, that you are getting what you want. When we took the limit of the area underneath these things, we got closer and closer to the area under this diagonal line. That's what we wanted here. But when we take the length of all these little line segments, that does not get even in the limit. That does not approach the length of this line. Okay. It looks like it might, but it doesn't, okay, which is easy enough to see. So let's go back to this and see what was wrong with my thinking. Okay, does that help you see what was wrong? I don't know if it would have helped me or not. So remember what we have to do. We have to take this little length right here and we have to go all the way around with it. So the problem was in calling this little length a little dx. Because notice that you can have two graphs. You could have a graph that looked like this, or you could have a graph that looked like this. And notice that they have the same little dx right there. They're both over the same little delta. I'll call it delta x. but one of them has a much larger length than the other one. And I could have made, if the graph came down real steep, you know, it could be like this. You could get a whole lot of length in there, which it's not going to be anywhere close to this little delta x. And you're not going to make this length any smaller by breaking this thing up. If you break it up into little pieces, you're going to break this up into pieces, but the sum of them is still going to be long. Okay, you're not going to make it short just by breaking it up into little pieces. The point is, we have to take that length into account. We have to actually ask, what's the length of that thing, and we're going to take that all the way around. The good news is we've already done it, right? Do you remember? If you have a curve like this, I'll push it out just a little bit, and this is delta x, and this is delta y. Then the length of this hypotenuse is close to delta x squared plus delta y squared. And so that's what we're after. That's the length we want. That's the length we want. So our surface area, our little piece of surface area, is going to be what we get by adding up, or I should say the surface area of the whole thing is going to be what we get by adding up these lengths. So each one of those lengths is like this. Delta x squared plus delta y squared. So there's the length. That's what we were after. And now you multiply that by the distance around. And what's the distance around? It's going to be 2 pi times the value of the function. So 2 pi times the value of the function. So there it is. And now we can go ahead and say, okay, there's the approximation. So the actual surface area is going to be what you get by taking the limit as delta x goes to 0 of this thing. You can bring the 2 pi out front anytime you want. Like so. And then you actually perform the limit. You're going to get 2 pi times the integral from a to b of f of x. And now I'm going to do a couple steps in one. I've done this enough now. I'm going to first factor the delta x out the back. And that delta x squared, when it comes out the back, it's going to come out as a delta x, or in this case it becomes a dx because I'm already taking the limit. And what are you going to have left inside? You're going to have a 1 right there. And then this is going to be delta y divided by delta x, which in the limit becomes dy dx. And dy dx is just the same as the derivative. So you're going to have the derivative squared. Okay, so I did about three things in once there. I pulled the delta x squared out the back, and then I took the limit, and so it became a dx. And when I pulled it out, I'm left with the 1 right there and the function right there. So there you go. So there's the formula. And again, it's one of those things that you realize it's going to be kind of a special function that I can do all this stuff and still get something that I can integrate and evaluate. Luckily, one of the most interesting problems to do is one that can be done. Okay, if you look at the headlights of your car, the headlights of a car are in the shape of a parabola. And the reason they're in the shape of a parabola is because a parabola has the unique property that if you have light shining right there in the middle of the bulb of your headlight lamp of the car, then that light, some of it will go straight out, of course, but others of it will go back. And when it goes backwards, then it hits the reflective rim of your headlight, and if it's a parabolic surface, then it heads going straight back out. No matter where it hits, that angle is just right so that it goes straight out, which is typically what you want. If you have headlight or a flashlight or something like that, and you want the beam just to be a nice, straight, narrow beam. Something like that actually works in both directions, okay? It sends the light out. Also, if you're collecting light. So, for example, the huge radio telescopes that one just collapsed here recently. I can't remember where it was. Was it down in South America? I can't remember. But these things are built and they're huge, and they get these radio waves that are coming from way, way out there in the universe someplace, very, very far, and they come in, and of course they're very, very faint, but you have this huge thing which is like maybe hundreds of meters across, the length of a football field, I think, across, and so they all come in, and they hit it, and they're all coming parallel, basically, because they've come such a long distance, so they're all coming parallel, and when they hit this parabolic curve, then they all jump right back, and they go straight to this point right there, and so that point is where you put the receiver, and you can collect all that information, and it's strong enough to be able to hear it. Okay, so that's the idea. You can also, if you've ever been at some of these amusement parks where they have a little parabolic wall like this, and then maybe 50 meters away they have another parabolic wall right there, and nothing in between, and you can have one person standing there and one person standing here, and they talk into the wall, and what does it do? It shoots it out here, comes here, and it bounces right to there. And anyone in the middle, they don't hear anything because all these waves are dispersed over that wide of an area. But once it comes here, then it all gets pinpointed right to there, and you're going to hear what the other person is saying. So it's kind of cool. So anyway, that's the whole point. So suppose we wanted to build one of those things. And so we build it by taking a parabola, and so let's go ahead and make a parabola like this. So let's just make y equal the square root of x, and so that's going to be a parabolic surface. By the time I go all the way around the x-axis with it and back up the other side, you're going to get yourself a parabolic surface. So we want to say we built something like this, and we want to line it with some very expensive reflective material. And so we want to know exactly how much of this reflective material to get, and so we want to know exactly what's the area of the surface. Okay, so that's what we're after. So let's go ahead and do it. Let's find the area of the surface of revolution by taking this thing right here all the way around. Let's suppose we go from 1 to, just to make it interesting, let's make it 1 to 4. So this is going to be the point 4, 4, 2. Not from 1, from 0 to 4. Okay, so from 0 to 4. So what do we do? Let's see. So for our case, it's going to be the surface area. It's going to be the integral from 0 to 4. And then it's, oops, I need a 2 pi out there. So it's going to be 2 pi. Integral from 0 to 4. Here's the function, which is square root of x. And then we have the square root of 1 plus the function, the derivative of the function squared. What is the derivative of the function? Well, let's see. This is y is equal to x to the 1/2. So the derivative is going to be what? 1/2 x to the minus 1/2. Agreed? There's the derivative. And if you square that, you're going to get 1/4 x to the minus 1, which is the same as 1 over 4x. So it's going to be 1 plus 1 over 4x right there, dx. So that's what we have to be able to find the antiderivative of. Do you see how to do it? Do you see how to do it? Take a moment and stop the video and see if you can do it on your own. Okay, this is something that requires a little ingenuity, a little algebra, and a little bit of other stuff. Okay, I'm going to assume you've tried, so I'm going to go ahead and do it now. So I'm going to go 2 pi. Here's the trick. The trick is to multiply these two things together. So you're going to get the integral from 0 to 4. If you multiply them together, it's all going to be a square root. It's going to be a square root of x here. And then you're going to have, this comes in as an x, and you're going to get x over x, which is 1. So it's going to be just x plus 1/4. Just x plus 1/4 dx, like that. There you go. And so now we need to find the antiderivative of that. And you see how to do that one? That one is going to be, you can do a u substitution. I'm running out of space here. I'll do it up here. So u is equal to x plus 1/4. So du is equal to dx. And so this whole thing becomes, I still have my 2 pi out front. Integral, it's going to be square root of u du. So in other words, it's u to the 1/2 du. And how do the limits of integration change? When x is equal to 0, when x is equal to 0, u is going to become 1/4. And when x is equal to 4, what's u going to become? This is 16/4 plus 1 is 17/4. So 17/4 like that. So there you go. Now we can go ahead and evaluate it. It's going to be 2 pi. This is going to be u to the 3/2 times 2/3, evaluated from 1/4 to 17/4. And just like I do in my class, I'll let you finish it off. This is going to be 4 pi over 3 times, well, shoot, I guess I'm doing it for you. So what do? You put 17/4 to the 3/2, 17/4 all to the 3/2 power, minus 1/4 to the 3/2 power. I guess I'm going to have to get rid of some of this. There you go. And there's your final answer. Okay? You could do a little more simplification there. Let's see. I'll just leave it like that. Okay? So there you go. So that's an example of using finding the surface of revolution. Now let's do one more. Now that you know how to parameterize surfaces, let's ask, what's the area of the surface of a sphere? Find the area of the surface of a sphere. Let's say of radius r. Okay? Radius, area of the surface of the radius of the sphere of radius r. So, let's see. Let's first put it in parametric equations. So remember how you do that? If you want a sphere of radius r, you're just going to have x of t is equal to r cosine t, and y of t is equal to r sine of t. And we want to take just this top half all the way around the y-axis. And so the top half we would get as t goes from 0 to pi. When t goes from 0 to pi, you're going to trace that whole thing out. So you'd say t goes from 0 to pi. So that takes care of that. Now we also need the formula for the surface area. And I'm going to leave this to you. Okay, we've done all the pieces, so I'll let you verify this, that the surface is going to be this. The surface area is going to be 2 pi times the integral from 0, or in our case from 0 to pi. Now, what do we want? For every value of t, we want the distance around is going to be 2 pi times the radius. And if you're at this value of t, which brings you right up to there, we want this height, because that's the distance, that's what's going all the way around the x-axis. So this right here is your y of t, right? That's the y of t, so I'll write y of t here. And now that goes all the way around, but now I have to multiply that by this little distance. And that's the part I'm going to leave you with. If you remember from when we did this with arc length, we ended up with, when we had parametric equations, we ended up with dx dt squared plus dy dt squared. That was the little bit of arc length that we had, and it's going to be exactly the same thing here. Our little bit of arc length is dx dt squared plus dy dt squared, all times dt. Okay, so there's your formula. There's your formula, so let's go ahead and do it. Let's see what we get. So it's going to be 2 pi times the integral from 0 to pi. Y of t is r sine of t. Okay, now we have dx dt. What's dx dt? It's going to be negative r sine of t. So it's going to be negative r sine of t, quantity squared, plus dy dt, the derivative of y, is going to be r cosine of t, quantity squared, times dt. So notice I have r squareds in here. The r squareds can come factoring out. If they come factoring out, they're going to be an r. So I'm going to have an r when these come out. Here I have another r, so r times r is r squared. So let's pull all those out. It's going to be 2 pi r squared. Okay. Once I factor all those r's out, the square, first of all, makes this negative go away, and I'm going to end up with a sine squared t plus a cosine squared t. Sine squared plus cosine squared is equal to 1. So after factoring the r out, this whole thing just becomes a 1. And so I can disregard it, and all I have left is the sine of t. dt from 0 to pi. And you remember what the area is under the sine graph from 0 to pi? That's one of those that I think is just kind of worth remembering. I'll let you finish it on your own. The antiderivative of the sine, shoot, I'll just do it for you. It's going to be 2 pi r squared. The antiderivative of the sine is the negative cosine of t. Evaluated from 0 to pi, you're going to get 2 pi r squared. You stick in a pi here. The cosine of pi is -1. Negative times negative is a +1. Stick in a 0 here. You get a 1. Cosine of 0 is 1. So now I'm subtracting this -1, which gives me a positive. And so that gives me 2 times this is going to be 4 pi r squared. And that's the area of a sphere of radius r. Okay? It's kind of cool. Okay, very good. So, by the way, just a little bit of trivia. What's the ratio of the area of a basketball net to the cross section of a basketball? Okay, it seems like they're pretty close, but actually they're not. You can almost fit 2 basketballs together inside the net. Not quite, but almost. And if you figure it out, that means that that the area of the hoop is 4 times the cross-sectional area of a basketball. It's 4 times, which means that the area cross-section of the hoop is the same as the surface area of the basketball. Okay, very close to the surface area of the basketball. It's kind of cool. Okay, why do people not make shots all the time, given that there's that big of a hoop to shoot it through? I just don't know. Okay, very good. Next time, we'll get on to something else. You'll see.